Hello everyone. So this is the ninth installment of this organometallic class that is noted as transition metal organometallic chemistry, its principles to applications. So this is Anuv Nath. I am currently a PhD student at IIT Kanpur in the Department of Chemistry. So today we'll actually go through several examples that I have formed regarding these organometallic compounds, their structures, reactivities, and geometries. So in this case, I have actually today we'll be mainly focusing on the topic of metal carbonyls. So how they are actually bonded, how metal carbonyls react with each other, or how this they can be actually monitored, or how their reactivities differ with regarding to the metal centers that will be discussed. So firstly, the first example is regarding that is the geometry of VCO whole 6, that is the vanadium hexacarbonyl. This is firstly before going to any of these transition metal organometallic complex that is having a metal carbonyl bond, we will have to calculate the total number of valence electrons. So CO is actually two electron donor, that is a neutral moiety, and in this case, or in every other case where only COs are present in this transition metal complex, the metal is actually residing in its low oxidation state. So the electronic charge on the metal center is actually quite high in this case. That's why COs molecules are do come into picture, because they are highly pi acidic ligands. They can drag the electron density from the metal center in a convenient fashion. That's why the high electron density from the metal center gets distributed in the CO frameworks. That's how the metal complexes are stable. So low valent metal complexes are actually stabilized by these CO molecules. This vanadium is actually 4s2 3d3 system. So it's a D5 system in and COs are actually two electron donors. So six CO molecules will produce 12 electrons. So the total number of valence electrons in this case, 5 plus 12 is 17. So the 17 electron complex, the structures are actually given are multiple cases: pentagonal, pyramidal, trigonal, prismatic, octahedral, or planar hexagon. So the correct answer is octahedral. VCO6 having six CO molecules will be four will be in the equatorial plane and two will be in their axial position. So VCO whole six is an octahedral moiety. The second question is regarding the oxidation state of titanium in TiCO whole 6 2 minus. So the first option, the options are 0, plus 4, plus 2, or minus 2. Titanium is for a 2 D2 system, and they are having 2 electrons more, so D4, and in this case CO6 CO molecules will be there. 6 CO molecules are there. So 6 CO will be delivering 12 electrons. So 12 plus 2 negative charge, that is 2 plus 4 electrons from titanium. So the total number of valence electrons in this case is 18. And if we assume the oxidation state of titanium as X in this molecule, so X plus COs are actually neutral. So X plus 0 is counting towards minus 2. That is the total charge of the complex. So X is minus 2. So the charge of the oxidation state of titanium in this molecule is minus 2. Because you can easily see, if titanium, the total charge of the molecule is minus 2, and if COs are neutral, so the charge will be originating from the metal center only, that is minus 2. So the oxidation state of titanium is minus 2 in this case. The third question is regarding identification of the incorrect statement or statements. So this is an MCQ or MSQ, both can be possible. So the options are: firstly, the sigma bond arises from overlap of sp hybridized electron pair on carbon atom of the CO with empty metal d orbitals. The second option, filled d orbitals of metal back donates to pi star orbital of carbon atom of the CO. CO is a poor pi acceptor ligand. The last option is metal in high oxidation state is necessary for the formation of metal carbonyl compounds. So the correct options, actually the incorrect statements in this case, are option C and D. That is, CO is a poor pi accepting ligand and metal in high oxidation state is necessary for the formation of transitional metal carbonyl compounds. So we will go through one by one the each options. Option A, sigma bond arises from overlap of sp hybridized electron pair on carbon atom of the CO with empty metal d orbitals. The option is actually correct because in this CO there is actually triple bond in you will be seeing in one of the resonance structures. So the carbon is sp hybridized in this case, and carbon is having a negative charge and oxygen will be having a positive charge. So C minus, that is the sp hybridized electron pair residing on the carbon atom, will be then directed towards the empty metal d orbital. So they will be having an head-on overlap. So the sigma bond will be arising from that. In the second option, the field d orbitals of metal back donates. This is actually true because in this case, the metal d orbitals that are already filled will be back donating the electron to the LUMO, that is the pi star of the CO, that is typically based or mainly based on the carbon atom or carbon centered. The HOMO and LUMO both in the case are actually carbon centered. So in this case, the field d orbitals of metal will be back donating the extra electron density to the pi star LUMO of the carbon of the CO. So these two are actually indeed correct in terms of bonding of the metal orbitals with the CO orbitals. But option C and D are not correct because CO is a poor pi axial ligand. That is not true actually, because CO is a very strong pi axial ligand. If you have a glance at the spectrochemical series, you will see that CO molecules are very high pi acceptor ligand, because in the resonance structures of the one of the resonance structures of CO, you will be watching that C is having a negative charge and triply bonded to oxygen, and oxygen is having a positive charge. Oxygen already has a Pauling scale electronegativity in the range 3.5, and if you are having a putting a positive charge on oxygen, then it will be acting as a more electronegative element. That's why the pi acceptor ligand, that is the electron density dragging property of CO, is more. That's why it's a very strong pi acceptor ligand. But in the option D, metal in high oxidation state is necessary for the formation of metal carbonyl compounds. That is not true, because in the last example I have said that these COs are actually neutral ligands. They are very good by acidic ligand. That is, they are very good at dragging the electron density from the metal center. So think, if the metal is in high oxidation state, that is, metal is actually electronically deficient, and if COs are there, they will be dragging the electron density more and more from the metal. So the devoid or the deficiency of charge will not be stabilized by the action of CO, because they will drag the electron density more from the metal center. But if the metal resides in its low oxidation state, that is, metal is having an extra electron density, then the electron density on the metal center, that is not actually good, because metals are electropositive in nature, and if we are putting an extra electron density on the metal center, it will be not good for a metal. So in this case, the pi acceptor property of the COs come into picture. So the CO molecules will then drag the extra electron density of the metal center towards them. That's how they will be stabilized. So metal in low oxidation state is required or is necessary for the formation of metal carbonyl compounds. So option C and D are actually incorrect in this case, because CO is not a poor biacceptive ligand, it's a very strong biacceptive ligand, and not metal in a high oxidation state, but metal in a low oxidation state is necessary for the formation of metal carbonyl compounds. Now in this slide, before going to the calculating the total number of metal bonds of an organometallic complex, or total number of metal, how we will calculate, because in the later slides we will have to calculate a lot of them. So before jumping to that part directly, I have actually made this slide by which you will understand how we are going to calculate the total number of metal bonds in an organometallic complex. So one by one we will go. Firstly, determine the total number of valence electrons, that is TVE, in the entire molecule. That is the total number of valence electrons from the metal, plus we will be adding the total number of valence electrons from each ligand, and then the total charge of the molecule. So we will denote it as A. So A is TVE. So now we will subtract this number from 18N, where N is the number of metal atoms in the complex. So that is 18N minus A. So we will denote it as B. So B is 18N minus A. Now if we divide B by 2, then it will give us the total number of metal bonds in the complex. So after reaching B, we'll have to divide B by 2. That will be denoting the total number of metal bonds in the complex. But not only the total number of metal bonds is required, but also number of bonds per metal is also required, because then only we can actually draw the structure of the complex. Now if we divide A by N, then it will be giving the number of electrons per metal. So if the total number of electrons is 18, then there is no metal bond. If it is 17, then we will divide, so we will divide the number from 18 in each case. So if the number is 18, so 18 minus 18 is 0. If it's 17, so 18 minus 17 is 1. So there will be one metal bond. So if the number is 16, so we'll subtract 18 from the number. 18 minus 16 is 2. So that will be two metal bonds. So you can actually derive the formula from here only. You can see it is 18N minus A, that is actually B. Now if we divide the both LHS and RHS of the equation by N, we will obtain 18 minus A by N is B by N. So if A by N is already 18, so 18 minus A by N is 0. So B by N will be equal to 0. So N cannot be 0, because N is defined as the number of metal atoms in the complex. So A, B will be 0. So the number of metal bonds will be 0. So there will be no metal bond in the compound. So by this way, we can actually calculate the total number of metal bonds in the complex, and also the number of metal bonds per metal. So by having a glance at this formula, we will jump to the next slide, where we have several compounds. All of them are organometallic compounds, metal carbonyls. So we'll calculate how many number of metal bonds are there, or how many bonds per metal are present. Now, in this case, the question is as such: predict the basic geometry around the metal centers in the following complexes. Options are Fe3CO whole 12, CO4CO whole 12, eta 5 CpMO CO whole 2, that is also whole 2, and eta 4 C4H4 whole 2, Fe2CO whole 3, and the last option is Fe2CO9. So we'll go one by one. In the first option, this is the Fe3CO whole 12. That is total number of valence electrons you have to calculate. Just we have gone in the previous slide. So in this case, firstly, iron is in zero oxidation state. Iron is a D8 system because it is 4s2 3d6. So 8 into 3 is 24, and COs are 2 electron donor. So 12 into 2 is 24. So 24 plus 24 is counting towards 48. Now we are having A equal to 48. Now the formula goes as, we have to calculate B. B is defined as 18N minus A. So N is 3, because total number of iron atoms is 3 here. So 18 into 3 is 54 minus 48, that is A, is 6. So total number of metal bonds is B by 2. This is B, that is 6. 6 by 2 is 3. Now bonds per metal is also required in this case to have a brief core structure idea of the complex. So in this case, A is 48. We'll have to divide A by N, that is 3. So 48 by 3 is 16. We have to subtract the number from 18. So 18 minus 16 is 2. So total number of bonds are 3, and bonds per metal is 2. So here the core structure is as such, where three iron centers are singly bonded to each other. You can see that the total number of bonds are 3, one between this, one between this, one between this. So there is actually 3 metal bonds are there, and all the iron atoms are having 2 bonds. So per bond metal, so bonds per metal are 2. So they are having, this iron has 2 bonds. This iron has also 2 bonds. This iron has also 2 bonds. The next example, CO4 CO whole 12, that is tetra cobalt dodecarbonyl. So cobalts are actually having 4s2 3d7 system in zero oxidation state. So this is D9 system. So 4 into 9 is 36, and 12 CO will be producing total 24 electrons. So 24 plus 36 is 60. Now we have to subtract the number from this 18N. where n is 4 because total number of metal atom is 4. So 18 into 4 is 72 minus 60 is 12. Now the total number of metal bonds, that is B by 2. In this case you have to calculate 12 by 2 is 6, because B is 12, so 12 by 2 is 6. And we have to also calculate bonds per metal. So A is 60, to divide 60 by the n, that is 4, so it is 15. So 18 minus 15 is counting towards 3. Now the total number of metal bonds is 3 and bonds per metal is 3. So now we have to actually have an idea how the code is actually looking like. You can see the total number of metal bonds is 6. So if we are having this tetrahedral kind of structure among all the cobalt atoms, so you can see there are 1 bond, 2 bonds, 3, 4, 5 and 6. So total number of bonds is 6 and the number of bonds per metal is 3. So you can see here from this cobalt there are 3 bonds, 1, 2 and 3. From this cobalt there are actually 3 bonds, 1, 2 and 3. From this cobalt there are 3 bonds, 1, 2 and 3. And from this cobalt also there are 3 bonds, 1, 2 and 3. So all the conditions have been satisfied by the structure. Total number of bonds is 6 and the bonds per metal is 3. So the structure of the code is this one. Coming to this part, the question, the next example, eta 5 Cp MO CO whole 2, that is whole 2. So you have to calculate this case. In this case, the molybdenum is plus 1 oxidation state, because you have to think that eta 5 Cp is an anionic 6 electron donor ligand. So it is a negatively charged molecule. So molybdenum is actually in its plus 1 oxidation state. Molybdenum is actually residing in its chromium, molybdenum and tungsten. Chromium is a 4s, it is D5 4s1 system. So molybdenum 1 is a D5 system, that is 5 electron donor species. So 5 from this, eta 5 Cp is a 6 electron donor. So 6 plus 5 is 11 and 2 CO molecules are there. So 4. So 11 plus 4 is 15. There are 2 such fragments because it is whole 2. So 15 into 2 is 30. So A is 30, total number of valence electrons. And now we'll calculate B, that is 18N minus A. Total number of metals, molybdenum is 2. So 18 into 2 minus 30 is counting towards 6. And total number of metal bonds is 6 by 2, that is 3. And also we have to calculate the bonds per metal, that is 30 by 2, there was 2 is the number of metal atoms n, so it is 15. So 18 minus 15 is counting towards 3. So total number of metal bonds is 3 and also the bonds per metal is also 3. So then think in the way like if there are 2 metal atoms and the total number of metal bonds is same as the bonds per metal, then the metal will be actually triply bonded to the directly to the metal center. So there is actually a multiple bond character between the two molybdenum centers. So this is the core structure of the molecule where molybdenum is triply bonded to molybdenum. Total number of metal bonds is 3. Also bonds per metal is 3. Let's come to the next example. So this is eta 4 C4H4 whole 2 Fe2CO whole 3. Iron, 2 iron atoms are there. So it will be giving total 16 electrons because iron is a D8 system. CO molecules are 2 electron donors, so 3 into CO is 2, so 6 electrons, so 6 plus 16 is 22. And this eta 4 C4H4, this molecule is a special case. In the last example I have actually stated how these cyclobutadiene molecules are actually to donate the electrons. All the carbon atoms are involved in donating, so they are actually having 2 pi bonds, so they are actually donating 4 electrons. 2 such molecules are there, so total number of electrons donated by these moieties are 8. So 8 plus 8 plus 16 plus 6 is counting towards 30 electrons. So now A is 30. Now B is 18N minus A. 18 into 2 minus 30, that is 6. Total number of metal bonds is 6 by 2, that is 3. And also the bonds per metal, that is 30 by 2 because 30 is the A and N is 2 is 15. So 18 minus 15 is 3. So just like the previous example, here also you have to think the total number of metal bonds are 3 and also bonds per metal is 3. So they are actually directly triply bonded between the 2 iron centers. So Fe triple bond Fe is the core in this system. In the last example, that is diiron nonacarbonyl. In this system, they have to calculate total number of valence electron. A is 2 into 8 plus 9 into 2, that is 16 plus 18, that is 34. So the B, that is the total number, 18n minus A is 18 into 2 minus 34, that is 2. So B by 2 will give the total number of metal metal bonds, that is 1. And also the bonds per metal, that is 34 by 2 is 17. That is this is sorry for the mistake, because it will be actually 17. This mistake is written as 16. So 34 by 2 is 17. So 18 minus 17 is 1. So in this case also you have to think that this total number of metal metal bonds and bonds per metal are equal. So there is a single bond directly between two iron centers. So the core actually consists of a direct metal metal bond between two iron. So here I have actually gone through several examples to make you understand how their basic geometry of metal atoms can be determined simply by counting the total number of metal metal bonds and bonds per metal with the analogy from the last slide. So here also you have to calculate like this way. In this convenient manner, you can easily calculate the total number of metal metal bonds, and you have to predict the basic geometry of the core of the metal complexes. So this is the next question, where the prediction of the structure will be there of the molecules M2CO whole 10, where M is manganese, technetium or rhenium. These are actually in the D block element from the late transitional metal. You are actually in the group we have actually gone into. It is the manganese, technetium, rhenium group. Here to predict the structure of the, we have to predict the structure. In this case, that is M2CO whole 10, where M is manganese, TC the technetium or rhenium. So in the, so right now these we are deciding in the position where this manganese, technetium, rhenium group is present. What is the 4s2d, that is the ns2d5 n minus 1 d5 system, where the compounds are actually residing in its zero oxidation state. So we have to calculate the total valence electron of the compound first, that is A. So A in this case is 2 into 7, because it is a S2D5 system. Total there are 7 electrons. So 7 into 2 plus 10 into 2. So 2 electron donors COs are there. So 10 into 2 is 20. 20 plus 14 is 34. That is A. That is the total number of valence electrons in this system. The 18n is there. 18n is 18 into 2, because there are two metal atoms. So 18 into 2 is 36. So we will calculate B as 18n minus A is 36. That is 18 into 2 minus 34. That is 2. So the total number of metal metal bonds is B by 2. That is 2 by 2 is 1. And number of bonds per metal, that is B by N, that is 2 by 2 is equal to 1. So we have to think in the following fashion: the total number of metal metal bonds is also 1, and just like the previous case, number of bonds per metal is also 1. So in both the cases, the total number of metal metal bonds is 1, and they are directly bonded to one another, just like the previous example where iron and chromium systems were present. So here you can see there are total 10 CO molecules are there. So 5 COs are actually bonded to this manganese, and 5 COs are bonded to this manganese. So they are actually single bond. So the structure of the molecule is as follows: this Mn singly bonded, and 5CO to this fragment, so 5CO in this fragment. So basically Mn2CO10 or any cast M2CO10 is a it's a joint venture of this MCO whole 5 moiety. This MCO whole 5 moiety. MCO whole 5 moieties are M, that is 7, and from 5CO we're having 10 electrons. So 10 plus 7 is 17. So 17 plus 17 fragments is 34, and between this metal metal bond is there, so there are 2 electrons, that is 36. So this is 36 electron system. So total there are electrons are, so it is actually obeying the 18 valence electron shell rule. This MN-MN bond can easily be cleaved in presence of oxidant, that is Br2. So it can by if we treat Mn2CO10 by Br2, so oxidative cleavage of this MN-MN bond occurs, and we produce two molecules of MnCO5Br. MnCO5Brs are also a Mn1 system. So from Mn0 we are going to Mn1. So that it is an oxidative cleavage where this MN-MN bond is cleaved and Mn is going from its 0 to +1 oxidation state. Now we'll come to this next slide where we have to compare the structures between M2CO9 and M3CO12, where M is iron or osmium. Here also in this case you can see this M is between 2 M2CO9 we have to predict the structure, and between 2 M3CO12 we have to compare the structures. So in the first case M is actually iron or osmium, both are actually residing in the D8 system. So 8 into 2 is 16 plus 9 into 2 is 18. So 18 plus 16 is 34. In this case 3 into 8 is 24 and 12 plus 2 is 24. So 24 plus 24 is 48. So 3 into 18 is 48, 54. 54 minus 40 is 6. 6 by 2 is 3. So there are total number of metal bonds is coming here as 3. Now what happens in this case? So firstly, we have to compare between M2CO9, where M is iron and osmium. So in case of osmium, you see in both the cases there are 34 electrons. So if we subtract 34 from 36, then we are having 2. So 2 by 2 will be giving us 1. So 1 is the counting towards one metal bond. So both OH2CO9 and Fe2CO9 has one metal bond present, Fe and OS bond. But the structure comparison lies between the number of carbonyls that are bridging or terminal. So in this case, you can clearly see number of bridging carbonyls 1. Only one CO is bridging. But in this case, you can see 3 COs are bridging. Here 1 CO, and there are 2 CO molecules are there. So you have to remember, or you have to remember the fact that the number that are the lighter members or the lighter congeners in this transitional metal are actually prone to have breach between themselves, but in the heavier congeners they are actually not they're not prone towards going to bridges. So number of breach in this case is lower for osmium, but number of bridging carbonyls here in case of iron is greater, that is 3. Now in the next example you see there are OS3CO12 and iron 3CO12. And in this case, if it is OS3CO12, then you see there should be 3 metal bonds, because if we calculate the number of electron, 3 into 8 is 24 and 12 into 2 is 24. So 24 plus 24 is counting towards 48 electrons, and 48 electrons if we subtract it from 18n, so 18 into 3 is 54. 54 minus 48 is 6. So if we divide 6 by 2, it is 3. So there are total 3 metal bonds that are actually present. So you can see in both the cases there are 3 metal bonds, and bonds per metal is also 2. And so in this we have actually discussed this example in the previous slide. So here you can see there are no bridging carbonyls between these osmium moieties, because I have already stated the number of bridging carbonyls is less for the molecules where the heavier congener is present. Osmium is the heavier congener. So in this case, number of centers are actually, in the case number of bridging carbonyls is less, so there are actually 0 bridging carbonyls. But in this case, there are two iron centers, and iron have being a lighter congener, they are prone in having forming the bridges. So they are actually having in the structure, you can see there's a crystal structure of Fe3CO whole 12, where two CO molecules are bridging between these two iron centers, but this CO does not have any bridging carbonyl. So all the iron atoms in this case are not equivalent. So these two iron atoms are equivalent in nature, and they are having two CO bridges. Now the main question arises here, why we are very prone in understanding the bonding in case of metal carbonyls only. Why extensively we should study about metal carbonyls, how their bondings are affected or else. So firstly, we will go one by one. This is the molecular orbital diagram of CO that is here and that is depicted here. You can have a look. In the left hand side, we are having the less electronegative element, that is carbon, that is having a 2s2 2p2 electronic configuration. The 2s having deeply seated, having the energy minus 19.5 electron volt, and the 2p's are comparatively higher in nature because they are away from the nucleus. So it is having electronical energy minus 10.7 electron volt. Likewise, the oxygen here, the 2s of oxygen is having minus 32.4 electron volt. 2s2 2p4 is the electronic configuration for oxygen, and in this case the 2s 2p4 is having a electronic energy minus 15.9 electron volt. Now the question arises, why does CO bind a metal through its less electronegative carbon atom than its more electronegative oxygen, and why it is such a good pi acceptor? So in this case, you see the main question arises here is that why CO having these two electronical two atoms kinds of atoms are there. Carbon that is more electropositive and oxygen that is more electronegative. Carbon's electronegativity lies in the range 2.5 to 2.8, and in this case oxygen is having a high electronegativity in the Pauling scale, that is 3.5. So why being the more electronegative oxygen atom does not bind to the metal center, but the less electronegative carbon center bind to the metal centers? This is the question. We have to discuss the fact. So if we are having this molecular orbital diagram, you see in the left hand side we are having these four orbitals, in the right hand side we are having four orbitals. Now we have to make it between these 2s and these 2s of this CO and this CO of this, they are having these are actually having this sigma property, because all these oxygen 2s and carbon 2s are having more prone towards forming sigma bonds. So one sigma and the sigma star, two electrons are there, so two electrons incoming in this lower bond, lower orbital, two electrons in the sigma star orbital, so four electrons are filled here. But in case of 2p of the carbon and 2p of the oxygen are far apart from one another, so they are having total six orbitals. So two are actually bonding, in this case pi, this is the sigma homo, this is the pi star lumo, this is the sigma star. So in this case also we are having total 2 plus 4 6 electrons, so each orbital can contain 2 electrons. So in this lower pi bonding mo, the 4 electrons are put, and in this case 2 electrons are put in the homo, that is a sigma. So the sigma is the homo and the pi star is the lumo. So this pi star is actually forming between this 2p of the carbon and the 2p of the oxygen. So this you can see, that is the homo, that is the sigma, and is the lumo, that is the pi star, all are actually based or concentrated towards the carbon atom. They are far away from the oxygen atom. That's why the homo is having a significant amount of carbon character. The government of carbon on the homo is much more efficient or superior to that in the case of oxygen. So the carbon is specific in binding to the metal center towards the sigma homo of the molecule, that is centered towards the carbon atom. Also the lumo is having a pi star lumo. This pi star lumo is significantly lower in character. This sigma star is so high energy that the electron cannot go to that much high energy extent, and in this case the pi star lumo is there where the CO can accept the electron. That's why it is a very good pi acceptor. So now we will read this. The highest occupied molecular orbital or homo of CO is weakly antibonding in nature. You see the sigma homo is having a significant amount of antibonding interaction with the pi star, that is compared with the oxygen atomic orbitals, and is an MO which is carbon based. I already said, because this MO is the homo is actually very close in proximity in the energy level with the carbon orbital. That's why in the carbon atom is donating to the metal center than its electronegative oxygen counterpart. But in the second case, the pi star antibonding orbital, which is the lowest unoccupied molecular orbital, that is LUMO, and HOMO is the highest occupied molecular orbital, that is HOMO. So pi star antibonding orbital in this case is LUMO. So lowest unoccupied molecular orbital is comparatively lower in energy. You see, this is comparatively lower energy than the corresponding sigma star. So which is make possible to interact with the metal T2G orbitals for pi bonding. So this pi star LUMO can interact significantly with the T2G molecular orbital of the metal center. So there exists a significant amount of back donation from the T2G metal orbital to the pi star LUMO of the CO. So there occurs a significant kind of molecular orbital pi bonding interaction with the pi star of the CO. That is actually again carbon based. So in this case, we are actually going to two facts. That is, this is the reason why CO is a very good pi acceptor, and also it is prone to bind to the metal center by the carbon atom, not the oxygen atom. So the in the molecular orbital diagram of CO, here lies the answer. Now we are actually going to some specific examples where we are to go through different kinds of bridging modes of CO in metal carbonyls. So metal carbonyls can be bound to the metal center, or they can form several kinds of bridging modes of CO, or there can be several kinds of binding modes also. So you see, first one is the eta 1 terminal binding. Here you can see only one carbon atom is bound to the metal center. So only one center is actually bound to metal. So it is a eta 1. Its terminal position CO is there, so it is terminal binding. CO can potentially bridge between two or more metal atoms. You see in the later two examples, CO is bridging between two metal centers. So it is doubly bridging mode. That is the eta 2 mode, because CO is binding to two metal atoms simultaneously. This is a triply bridging mode. It's a eta 3 mode. The C is bounded towards three metal atoms simultaneously. So it is eta 3, that is triply bridging. There are actually several kind of CO bindings are there, where two eta 2 bridging can simultaneously be present in the moiety, and two eta 1 terminal binding can simultaneously present in the MCO binding. Here also you can see that is the MCO binding can actually be, there can be some intermediate modes of binding between terminal and bridging. You see this is a terminal binding, these are the bridging bindings. But there can be modes in cases where terminal and between the a difference or the intermediate mode of binding can be present, but there is nothing terminal or bridging also. So in this case, the metal atoms are bonded towards here, but the two CO that are bridging between two metal centers are not equivalent in nature. So in this case, there is an intermediate mode of binding where this CO is concentrated towards this metal, but this CO is concentrated towards this metal. And is also a specific example where in such it is actually same as this one, where there are metal bond present also. But in this case, what happens, two metal centers are bonded towards each other by the single sigma bond also, and by this eta 2 bridging also. So there can be such several modes of binding of CO in the metal carbonyl compounds. They can be terminal, or they can be doubly or triply bridging. This is another a very good example. The question is, can CO act as a 4 or 6 electron donor ligand rather than its conventional 2 electron donation? So the answer, you can see that yes, this can be possible. Unsymmetrical sigma or pi bridging in metal CO compounds are quite well known. There you can actually interact with the side-on coordination mode that I have not discussed till now. I have actually gone through only the terminal binding or the bridging binding, where COs are typically acting as a 2 electron donor. But here you can see COs can act as a 4 or 6 electron donor species. They are capable of doing such. There will be such unsymmetrical sigma or pi bridging. So let's go through the specific examples where we can see how these COs can manage such kind of unsymmetrical binding. So in this case, you can see the two metal atoms are bonded towards one another by single bond, and there is a CO molecule that is terminally eta 1 bridge to one of the metal centers. But you see there is a significant interaction of this metal center with this pi bond of the CO. Here you can see this COC is interacting with one of the metal atom, and the pi bond between this carbonyl is having interaction with the metal atom. Here you can see in this next example, this pi bond is having simultaneous interaction with the two metal centers, and this metal is actually having eta 1 terminal binding with the CO. And this is actually a very much rare example where you can see there are four metal atoms, and the carbon center is having carbon is having an interaction with the metal center, and also with this metal center and this metal center also, but there is a significant interaction with of the CO carbonyl moiety with the this metal center also. So there can be such several modes of binding where this unconventional 4 or 6 electron donation is possible. So these are actually having a side-on coordination mode with the metal center. So they are typically termed as side-on coordination mode, where not only the carbon of the CO is donating, but the pi electrons of the CO molecule bond is also donating towards the metal center. They are actually termed as unsymmetrical sigma or pi bridging, where 4 or 6 electron donation can be possible. So two specific examples I have denoted in this case, that is the Mn2CO5 moiety in this following compound, and also this niobium 3 mu CO moiety in this CpNbCO whole 2 whole 3 mu CO compound. Firstly, in this example, you can see there is a metal-metal bond, Mn-Mn bond here, having a bond distance 293 picometer, and they are each of the manganese are having two CO molecules. There is a CO molecule that is eta 1 terminally binding with the manganese center. This MnC bond length is 193 picometer, and this CO bond is 110 picometer. This C is having a significant interaction with the manganese. This oxygen is also having a significant interaction with the manganese. The C manganese bond distance here is 201 picometer, and the oxygen manganese bond distance is 229 picometer. So there is a significant amount of bonding character between this CO, between this Mn. So it's a 3-center 2-electron bond. This manganese, this carbon, and this oxygen of this CO is having a 3C2E bond here. So this is a specific example where CO is acting as a 4 or 6 electron donor with the aid of its side-on coordination mode. This is a specific example where CO is side-on coordinated with the other manganese also. This is also bonded directly to one of the manganese atoms by this eta 1 terminal bond. But also there is a side-on coordination mode with this manganese also. Both the CO atoms or the pi bond is having a significant interaction with the manganese atom. In this specific example, this is a niobium 3 cluster, NB having a 3 NB bonds, and number of bonds per NB is also 2. Here you can see there is a CO, and this CO is this niobium C bond distance is 197 picometer. Yes, you can see the CO bond distance is 130 picometer. You can see this oxygen is having significant interaction with these two of the niobium atoms. This oxygen niobium bond distance is 224 picometer. This bond distance is 221 picometer. So there is significant bonding interaction of the oxygen moiety with both of these niobium atoms. Also, this carbon is singly eta 1 bonded with this niobium atom, but it is also having a significant interaction with the two niobium atoms. So here on this case, all the bond parameters are not also given for the aid of clarity, but you can have a clear idea about that each of the cases these CO molecules are having an end-on or side-on coordination with the end-on coordinator mode. Also, it is having a significant amount of side-on coordination mode also, where not only with one metal center but with the side-wise metal centers also it is having a significant kind of interaction. That's why these are having a 4 or more than 2 electron donor possibility is here, because not only 2 but 4 or 6 electron donation can also be possible, where CO is unsymmetrically bonded by the bridging moiety between these MCO organometallic compounds. Here in this example, I have denoted like arrange the following species in their ascending order of these carbonyl stretching frequencies. In the first example, that is the compounds given are NiCO whole 4, COCO whole 4 minus, and FeCO whole 4 2 minus. The second example, compounds given are MnCO whole 6 plus, CrCO whole 6, and VCO whole 6 minus. So before going to the actual answer of this question, we have to go to the bonding properties of MCO bonds. In the previous example where I have discussed about the molecular orbital theory or the molecular diagram of CO, I have actually stated a bit of it, but here we'll elaborately see how this MCO bonding takes place. So in this first case, you see there is a metal CO bond where the CO 5 sigma is donating towards the metal sigma. So this is a sigma donor interaction bonding where CO centered HOMO donates the electron to the metal center. Then this is a pi donor interaction where CO1 pi will be donating the electron to the metal pi. But since the pi orbitals are actually far away or the deeply seated orbitals, so they will not be interacting. So they are actually often neglected here. So it is here written as often neglected. In this case, the CO2 metal interaction is there. In return, the metal filled d orbitals will be donating that extra electron density towards the 2 pi of the CO, and that is actually quite prominent because it is a pi acceptor back bonding interaction from the metal to the CO. That is elaborately discussed in the previous slide in terms of molecular orbital theory. So each of these bonding has significant effects on the MC or the CO bond. Here you can see because there is a MC triple bond O bond distance is there. So if we draw the resonance structure, M minus will donate the electron and C triple bond O will drag the electron density to the oxygen center. So M double bond C will be that will be bounded to double bond O. So the back donation is actually helping in strengthening the metal's carbon bond, but in weakening the CO bond. Now, if you see here, if the bond order MC, so the CO to metal, if the sigma bond is present, so the MC bond order increases. The bond order of CO, because the HOMO is anti-bonding or HOMO is cyclically anti-bonding in nature in CO. That's why if the electron density goes from the HOMO CO, that is the cyclically anti-bonding in nature, that also increases the CO bond order, and also the stretching frequency of the CO gets increased. In the second case, you see that is often neglected. That's why we will not discuss anything about this midway, that is the CO pi to metal pi interaction. But the last option is quite prominent when metal pi to CO2 pi interaction is present. So this is a pi acceptor interaction. If we see that is the metal to C bond distance is there. So if metal throws the electron density to the carbon center, in the resonance structure you see there is a double bond character between the metal C. So that will be dividing the increasing in the bond order. Also, if so, the C triple bond O will be ruptured, it will be producing C double bond O. So the bond order of CO will also decrease in this case, and also the stretching frequency of the compound will decrease. Now we'll come to the specific example. This is an increased negative charge that is leading to the expansion of metal d orbitals, that is implies increased metal d pi to CO pi star overlap. You see this is a D10 system, NiCO4, COCO4 minus and FeCO4 2 minus. You see, because the net negative charge is actually increasing in the order from NiCO4 to COCO4 minus to FeCO whole for 2 minus. All are D10 system, but the negatively charged species is actually having the highest electron density. That's why the negative charge density of throwing to the CO bond is actually highest in case of iron CO. That why the decrease is most in case of this iron CO. So the new CO stretching frequency is lowest in case of iron CO4 2 minus, that is 1790 centimeter inverse. You see the more negative anion is having a less electron density than the FeCO whole for 2 minus. So this also donates the electron to the CO, that is back donation, pi back donation, that is having a significant electron donation. But since it is negatively charged, it is not that much capable of throwing the electron. That is the new CO is not that much low, that is 1890. But nickel CO4 is a neutral species. So in this case, the new CO is highest one, that is 2060. The same actually goes in case of the option these cases where this MnCO6 is positively charged. So it is actually least probable that the electron density will be going from manganese to the CO, that is having the highest CO stretching frequency, that is 2090. In case of CrCO6, that is 200 lower than the manganese one, and in case of VCO whole 6 minus, that is 1860. That is the lowest one because it is having a negative charge, that is 1860. So in between this VCO6 minus and COCO4 minus, both are negatively charged. So you may ask the question, how it is a different? So VCO3 minus is 1860, in COCO minus it is 1890. In this case, the electronical, so we have to think in this way. Since this D6 electronical system, that is VCO6 minus, have a high electron density, that's why it can backdonate more efficiently than CCO whole 4 minus. That's why the electron density decrease is here is the most, not in case of this. Here also in this case you can see the CrCO6 and ICO whole 4 all are actually having this, are having a lower amount of new CO. It is neutral, it is also neutral. But how can you can do a comparison? In this case you can see as chromium is having a high electron density, that's why it is actually more efficient in backdonating the electron. That's why the new CO decrement is more, it is 200, 2000, but nickel CO4 is not that much, not like Cr, the electronicity is not like chromium. That's why the nu CO is greater than that of the CrCO whole 6. So these are the specific examples that I have actually accumulated, how these metal carbonyl saturation frequencies can vary according to their charge. In the last example, we are actually from the all the going through all the metal carbonyls, or in this case going to the metal carbines that I have discussed in the last slide. What happens when a metal carbine is reacted with a Bronsted acid? So in this case, what is the Bronsted acid is actually HCl or HF or HBF4. So it is a typical metal carbine where you can see there is a typical metal carbon bond is present, L and M, triple bond C bonded to R. So if we protonate this metal carbine by a Bronsted acid, that is either the Bronsted acid can be HF or HCl or HBF4. So what are the possible products? So there can be two possible pathways by the aid of which the Bronsted acids can act with the metal center. This is a soft M triple bond C in nature, and Bronsted acids are actually quite harder because H plus is quite hard in nature. So this H plus can typically be bonded to the pi electron moiety of this AM triple bond C, and it can be protonating the entire complex by increasing the charge by 1. And also this is the one of the case where the electrophilic attack of proton takes place in the pi bond between the M and C. And in the second option, what happens in this case, the X minus can actually can bind to the one of the metal center, and since this carbine moiety has a high trans effect, so it can actually throw out one of the ligand center that is neutral. So one of the ligand will be lost or dissociated from the molecule, and it will be denoted as Ln minus 1. And in the place of the L, one of the X will be bonded towards the metal center, and this H plus will be protonated here, and there the triple bond will be ruptured, and it will form a metal carbene system. So for by protonating this kind of metal M triple bond C, we can actually go from metal carbine to metal carbene. And also in such cases, if we can protonate this, the X minus can be liberated, and also this H can be interaction between this M triple bond C, making this a positively charged complex. So this protonation can happen both at the metal center and also at the carbon center. So this is all for today. All the contents I have finished for today. So now you can ask questions if you have any doubt regarding any of the slides.